friends, myself Pooja Gajanan Domkawade from BSc 3rd year Indira Gandhi Kala Mahavidyalaya Ralegaon, and I am going to deliver the seminar on the topic operator in quantum mechanics from Schrodinger's equation and its application. So, what is quantum mechanical operator? The physical quantities which are obtained by the measurement or by the process of observation on a physical system are called as observable quantities. Some examples of observable quantities: position coordinates, components of velocity, linear and angular momentum, energy are some of the example of observable quantities. We know that all the information of system is contained in the wave function psi. The observable quantities are obtained by the mathematical operation on wave function. This mathematical operation is called as quantum mechanical operator. For every classical observable, we have quantum mechanical operator. For example, consider a wave function psi in bracket x, y, z, t equal to a e to the power minus I upon cross h in bracket et minus bracket px dot x dot py dot y dot px z bracket complete. Equation 1, differentiating with respect to x. Now we get del psi upon del x equal to I upon cross h px psi or minus I cross h del psi upon del x equal to px into psi. Equation 2. Similarly, we have for y and z minus I cross h del psi and minus I h cross del psi upon del z equal to pz psi. Equation 4. Differentiating with respect to t, we get del psi upon del t equal to minus I upon cross h into e psi equal to I upon cross h e psi. Here I square equal to minus 1 or I cross h into del psi upon del t equal to e psi. Equation 5. From equations 2, 3, 4 and 5 show that observable quantities px, py, pz and e are related to differential operators minus I cross h del upon del x, comma minus I cross h del upon del y, comma minus I cross h del upon del z and minus I cross h del upon del t respectively. They are called as quantum mechanical operators for x, y, z components of momentum and energy. They are summaries in the table given below. Here table dynamical variable and quantum mechanical. From this we can obtain operator for kinetic energy. We have psi in bracket x, y, z, t equal to a into e to the power minus I upon cross h in bracket at minus bracket px dot x dot py dot y dot bz z bracket complete. Differentiating with respect to x twice. Del psi upon del x equal to in bracket I upon cross h into px psi and del square psi upon del x square equal to I upon cross h bracket square dot px square psi or minus h square into del square psi upon del x square equal to px square psi. So I square equal to minus 1 dividing by 2m on both sides minus h square upon 2m del square psi upon del x square equal to px square upon 2m psi. Equation 6. Now px square upon 2m is x component of kinetic energy. Therefore minus h square upon 2m del square upon del x square is quantum mechanical operator for x component of kinetic energy. In order, Word's operation by operator minus h cross h square upon 2m del square upon del x square yields x component of kinetic energy. So kinetic energy equal to T equal to Tx square upon 2m. In quantum mechanical operator, T shows in cap. So T cap equal to minus h minus cross h square upon 2m into del square upon del x square is equation 7. For 3 dimensions, T equal to minus cross h square upon 2m into delta square, equation 8. In classical mechanics, the total energy given by Hamiltonian function H as H equal to P square upon 2m plus V, equation 9. Substituting the operator 2P square upon 2m equal to minus cross H square upon 2m delta square, the operator for total energy is given by H cap equal to minus H cross square upon 2m delta square plus V. This operator is known as Hamilton's an operator or total energy operator. Consider time-dependent Schrödinger equation. Minus h square upon 2m del square psi plus v psi equal to I s cross h into del psi upon del t. Replace with operations h and e. The above equation can be written as h cap psi equal to e psi, equation 10. That is when wave function psi is operated by Hamilton's by operator, we get the function psi multiplied by total energy E. The quantum mechanical operator for dynamical observable E is then Hamilton's an operator. In general, the quantum mechanical operator can be defined as a mathematical operator which, when performed on the wave function, transforms it into another function. Thus, if a cap OP is operator operating on wave function psi, then we have a OP psi equal to lambda psi, equation 11. The wave function psi which satisfies this operator equation is called as eigenfunction, and the value lambda is called as eigenvalue of the operator. The above equation is known as eigenvalue equation. The effect of operator is to multiply the function psi by a constant factor lambda. If instead of a single eigenfunction, then are several eigenfunctions corresponding to single eigenvalue satisfying eigenvalue equation, then that eigenvalue is said to be degenerate. The number of eigenfunctions corresponding to the particular eigenvalue is called as degree of degeneracy. Thank you.